Hi, everybody. Thanks so much for joining us. Um, Today, we are going to talk about neuroscience research tools, past, present, and future. Um, Welcome. My name is Matt Davis. I'm going to be your host today. We're going to be talking to Dr. Chris Freewen, who is a very gifted, creative person that we are lucky enough to have to work with here um, at NeuroNexus. And so we are going to continue our bi-weekly webinar series. So the next webinar is August 20th. I'm going to say it's tentatively scheduled just because you can't take anything for granted in these uncertain times right now. But Dr. Andreas Tolias from Baylor College of Medicine has agreed to give this next webinar. So that's going to be a great one also. And I did want to mention that, these are uncertain times, and one of the things that we can't count on is getting lab time all the time. So we did pre-record this interview with Chris because we didn't know if he was going to have lab time or not. So we're going to show you that, but he is going to join at the end and be able to answer questions. So I just want to give you a little bio of Chris, and then we'll start it up here. Dr. Christopher Freewen started his career studying microelectromechanical systems fabricated from carbon-based semiconductor materials. During these investigations, he worked as a visiting scientific researcher within prestigious international laboratories like Max Planck Institute in Stuttgart, Germany, and the Institute for Microelectronics and Microsystems in Catania, Italy. In his PhD candidacy, he focused his material science expertise to investigate material interactions with neural-derived cells in order to devise methods which would improve the chronic reliability of neural implants. Dr. Freewen became a National Institute of Health Ruth L. Kirchstein National Research Service postdoctoral fellow in the Department of Molecular Pharmacology and Physiology at the University of South Florida. He studied chronic glial response to microelectrode devices chronically implanted in the hippocampus and assisted in the design of electronics capable of simultaneous stimulation and recording to enable the bridging of neural signals across damaged brain tissue. He moved on to Dr. Jefferson Pancrazio's laboratory at the University of Dallas, Texas, where he was involved in investigating shape memory polymers and their ability to overcome micromotion damage, a major factor attributed to chronic neural implant failure. Currently, he is a principal engineer at NeuroNexus, where he uses his expertise to improve the reliability of neural implant devices for neuroscience and has the goal of enabling their utilization in translational clinical applications. I also failed to mention that Lawrence is going to be interviewing. He's going to be conducting the interview here. You'll see him in here. He will also be available for questions at the end if you have any questions for him specifically. So with that, I'm going to go ahead and mute myself and start the video.
Thanks, Matt. I appreciate that. We do have Chris here today. He's one of our PhDs. He's sitting, just a few feet away, more than 6 feet, of course. But today we're going to go through and start with a couple of questions. Chris, how are you doing today?
Doing very well. Thank you.
I guess some of the basic questions would be, what got you into science? How did you get to where you are? How did you become what you're doing? Where were your interests? Kind of what made you grow into where you are today?
Well, initially I was rather good at science. When I was in elementary school, I did the whole science fairs and won, and actually went to state and all of that. So Yeah, I've always been in science, but I was more really general back then. What really kind of solidified me was I really liked electricity. My mom, actually, we had a planetarium in Denver, big museum there, and they more or less put her in a Faraday cage and had a 12-foot Tesla coil discharging all over the cage. So I thought that was pretty cool. And, you know, they showed the trick with the, hey, look, we can power this fluorescent light bulb from across the room with the Tesla coil on it and stuff. So later on, after I graduated high school, I had done a lot of the sciencey and the AP and all that kind of stuff, and unfortunately took a little break and got a job because I wanted to make some money. I was an engineering technician for a while, making maps and stuff, doing computer programming, a lot of kind of eventually stuff that, you know, I didn't see have a future, so I decided to come back, and that's when we really solidified where I was at. I came back into electrical engineering thinking, now I'll just get my bachelor's degree and go and get a better type of job. But luckily I landed in a group that we were doing more or less materials research on semiconductor devices, and I really got interested in, here I had a lot of programming skills, but now I'm actually seeing how chips were made, MOSFETs and switches and all the rest of this, and that's what really got me interested. Eventually our group kind of, the money for materials was running low, so we decided, where else can we go to? And my PhD advisor really was like, bio. That sounds like a good idea. So at the time I had a class, and in that class, it was about 2006 was when I saw my first NeuroNexus electrode. It was on the screen, and it was more or less talking about, in the MEMS class, it was talking about how to make these electrodes and how they were both mechanical and electrical. And it got me interested. I was like, man, I could see us doing a lot of cool things with those. And yeah, so I started making my own, more or less copying NeuroNexus in a way. I didn't have any connection with NeuroNexus, but in a way I did now because I'm copying references. And yeah, that's how I got my start. And I started looking at, well, everybody says at this time there's a lot of papers at this time that was saying they're not really, none of the devices out there are really lasting a long time. They're definitely not for use in humans yet, and even for the neuroscience applications, if you planted these chronically, they had a very big variability of their reliability. I could plant them, they could last for a couple of days, or they could last for a couple of months, but it was always a roll of the die. So for my PhD, I started looking at materials as a biocompatibility thing. What makes biocompatible materials? I was looking at a whole bunch of different materials. I think I looked at over 21 different materials, from semiconductors to metals to polymers, all across the board, and trying to figure out what makes biocompatibility. And I was growing cells on them and looking at how the cells, I was using atomic force microscopy to actually try to probe how the cells are attaching to the surfaces. And so that's where we got into what's biocompatibility. And later on, that's when I started trying to make my own devices. And I joined the neuroscience crew. We were looking at learning and memory. And it was a lot of really involved applications with the hippocampus. They were more or less looking at different drugs and how they would affect a disease that's very similar to Alzheimer's called Angelman syndrome, but it affects little children instead. It's really tragic because you see the children have the same problems that the older people have with Alzheimer's. And they were working with that while I was just more or less learning electrophysiology and trying to improve ways that they could look at the brain. Eventually, we got into a DARPA project where I met one of my post-P, a guy I did a postdoc with, Joe Pancrazio, and we were looking at different materials altogether to improve the conditions of the implants. And from this point, we were looking at polymers, we were looking at metals, we were looking at whole bunches of different types of materials from A to Z. And this is where I met people like Stuart Kogan, who was working on different silicon carbides, and I was working on, I met others that were working on different polymers and from PDOT on down. And it wasn't soon after that that I got referred to Neuronexus after working there for a while, and I got to start working at Neuronexus and hopefully helping bring some of their devices into a more reliable thing and maybe in the future into humans. So that's how I got into this.
So my next question for you would be, microelectrodes have been in development for about 3 decades. Do you think that the pace of these has been fast or slow, or kind of what do you think about how these have come about so far?
Microelectrodes in general, I think, have been a slow development, but I don't think that's necessarily the fault of the people developing it. I think it stems from an understanding of people in engineering and people on the biological side. Years ago, it was very difficult to actually get, I was an engineer trying to work in bio, and it was very difficult for me to actually talk to neuroscientists about their work, and vice versa, they didn't understand me. For half of the time for my first postdoc when I was in a neuroscience lab with Dr. Edwin Weaver, it took a long time for both him and I to actually start figuring out how we, to talk to each other and go, oh, I see what you're saying, and he saw what I was saying. So part of that, I think, is just a communications level. As an engineer, we see a problem and go, oh yeah, we can design that, we can do this and do that, and we put it out. But we don't really understand, and I know this for a fact from a lot of engineers, that we didn't understand underlying biological problems and issues. So we might have the greatest design in the world, but it would cause, a terrible reaction later on down the road. And so later in my career, that's what I started looking at, was trying to look at both what's called the abiotic condition as well as the biotic condition. We want to look at things that were happening with the devices themselves. This could be just an interaction of different materials. Polymers and metals don't like to usually stick together for a long time. They delaminate, especially that's one of the biggest problems apparently see in metals is oftentimes the devices themselves come apart. And of course, that means your device has now failed and it's not going to work too well. Another thing is, hey, we put silicon in the body. Silicon itself is not bad, but when you get when it turns to silicon dioxide can dissolve, and then that causes biotic problems, which can lead to glial scarring and gliosis. So when you're looking at those type of things, you have to take all of that into consideration with your materials to try to get the reliability up. And I think that's what we're trying to do here at Neuronexus, is look at some of these issues, figure out how we can fix that reliability, and hopefully move things forward.
So after these decades of developments, what do you think still lies as the most challenging part to what you just described?
So there are ways that we're looking at to make devices better. And that's a big challenge, because when we have the neuroscience community saying, we want 1 million electrodes, we'll just say it's not really what they're saying, but they want a whole bunch of electrodes. And the problem is, okay, for each electrode, we have to have a specific area, or the impedance becomes too big. And if we don't, or we'll have to find a different material that enables us to be able to record that different impedance. Or now we have, let's say, 1,000 electrodes. How do you have all the wires that transfers? How do you get all of that connected to a chip to where you can record from? That all becomes the abiotic part of the engineering part that really, I think, is the biggest challenge right now, is the more and more of these wirings or more and more electrodes we keep putting on a chip. We also have to figure out how to get all of that out without having a head stage that's the size of the animal. There have been companies out there that I've seen one that had 1,000 connections, but the head stage was literally about that big. You try to put that on a poor little rat's head, well. So yeah, I'm just saying that in the future, as an engineer, that's the problem I want to solve, is to take all of that and make it so, we just have a single wire to put in, maybe 5 wires to put in, and then that runs everything from a little transmission. We also have people that are trying to work on wireless with its own problems and conditions, because when you have a wireless device, you have to get through all the layers of skin and scalp and even bone sometimes if that's where they want to put it. And that becomes a huge issue on transmission, power. Those are things we're trying to solve.
So why do you think that microelectrodes haven't taken off for clinical purposes? So I guess you kind of answered a little bit on that, but I guess just touching base on exactly why you think we're not there yet. But I guess more so the approach of what needs to be done to kind of tackle that border and get to that point.
Mainly it's longevity of the devices. And yeah, I covered it a little bit earlier, but when you put a device in and you only have it last for, let's say, 6 months, the federal FDA is not going to actually say, yeah, that's a great device. We're going to let somebody have a nice operation. We'll put that in and last for 6 months and then not work anymore. Not necessarily that they're not working, but they're not working as described. So oftentimes I do know that we do have companies that have actually, at least one company has had a microelectrode device put into humans. It runs on mostly LFPs and not action potentials, for the very reason that those can be read, for years, and may even be read by devices like NeuroNexus. The major problem I see with those kind of devices is they still cause the gliosis and the problems that this has been shown in many papers. What I think the future is taking devices and making them even smaller. I've been involved in research where we've shown that making devices smaller and actually improves their chances of being able to not cause the biological reactions. And if you can have then the device have no problems in the abiotic region, meaning the materials don't fail, they don't oxidize, they don't fall apart, then yeah, I think we can have implants that could last a long time.
So in the neuroscience field, there's been a growing trend to have devices with more sites and also be smaller. Some people saying that the ultimate quest is to go through and map the entire brain. What are your thoughts on that? And should technologists be going through and paying attention to this or wanting this? I guess what are the challenges behind mapping the entire brain?
Mapping the entire brain is going to be rather difficult just because, let's say, if it's a human brain, the size of the brain. So if we're making something smaller and smaller, now we have to devise methods to be able to get that into the brain to be able to map it. If it's for neuroscience and we're doing animal studies, even still in those, we're going to have to figure out ways to be able to reach the inner parts of the brain that, mostly cortical studies don't cover. So deep brain, more or less devices. With the kind of materials that we're using, then we have to figure out, okay, we have to have something that's a little stiff, or we have to be able to push it in with something that's stiff to get it in there, to then be able to map that area of the brain. And then how many electrodes do you include? How many electrodes is necessary to figure out the density of the cells, the activity? And I think that's why neuroscientists are saying, yes, we want more and more electrodes. And we also want to have electrodes of long sizes, short sizes, to be soft, to be able to be flexible. So it's a great deal, as a technologist, it makes a lot of challenges for me to try to figure out ways to meet all of those different types of requests and have an actual functional electrode that will last the experimenter's time while also being able to, hopefully move toward human translation. In my world, that's what I want to see is, yes, once we have the animals mapped, we need to start figuring out how the human brain works so we can start looking at therapeutics for a lot of the diseases and problems that humans have. So at least that's where I see my part in this, trying to figure out how that works.
So I guess my follow-up question to that would be, actually thinking about that, that's it's pretty futuristic, right? It's pretty futuristic to go through and want to map the entire human brain. But at the same time, even if we're looking at genome mapping, right? We thought that was outlandish until it happened. So what do you think something that could be the future of neuroscience? Why would you want to do those things? What benefits would something like that hold for the science community?
Well, just in the fact that, when I was working in Alzheimer's, or Parkinson's, for instance. These are two interesting diseases where you have parts of the brain that are degenerative. We have computers and stuff that can actually, we can intercept good parts of the brain and replace the bad parts of the brain, for instance, in my opinion. One of the things that I was trying to work on was called the brain bridge back in the day, where if the hippocampus was malfunctioning, we could still get more or less signals coming into the hippocampus, but parts of it were not working. We can intercept those with electrodes and then bridge it to a part of the hippocampus that still worked and have it function again. It may not be feasible for what I was doing back then, but I think as we go further into the technology, I think it will be. We have to get more electrodes, of course, but we also have to improve our way of being able to pull in the signals, quickly figure out what those signals want, and then being able to deliver something in turn. So that's also a software or a programming type aspect of this that I think I haven't been talking about now, but it's something that needs to happen as well. Once we have that, then you have a true brain-machine interface. And for people, we've had a lot of people in the past that have lost arms and legs, either through warfare or through accidents. We do have ever-increasing cybernetics that are able to be attached to people and give them some type of mobility again. But if you have a really good brain-machine interface, we can have those more or less machines almost replace your limb. They can have tactile, they can have temperature sensors, all that information can be put back in. And then the person wouldn't even be, wouldn't know that they lost their arm. They would think it was their arm or their leg again. For their eyes, for almost any type of sensory thing. I think that's part of the brain-machine interface that a lot of people don't look at fully. They think that's still science fiction, but there are people working on new eyes, new ears, and all the rest of that. And I think that's where I see us moving into in the future, and maybe even beyond that.
So looking at applications like you just described, so you're saying that you could essentially become like a cyborg. You could become like a sentient being just with the powers of neuroscience, if you will. Going through and kind of reiterating on that, what do you think a 10-year window would look like, a 50-year window? Like, where do you see these pieces of the puzzle finally coming together with the field that we have today?
Well, already we were talking how fast how fast this technology has developed. Computers have Moore's law, where every 2 years they were doubling their transistor size. With the electrodes, it's not as quick. It's about every 7 years, roundabouts, that we've been doubling our electrode size. So if you take the 1965 era, is more or less the advent of microelectrodes with wires in like 1970 with here at Michigan, where they started the silicon revolution with micro or thin film electrodes. If we take that into consideration and have it all the way up to today, we have devices out there that have 1,000 electrodes on them. So in 5 years, they have 2,000. We hope to speed that up, of course. I think 7 years is a little bit long, and that kind of goes back to an earlier question, how fast do you think things are going? I don't think they're going fast enough, but maybe, as more people get into this, like me, we'll try to get that speed going a little bit more and double. But with that, I think we can then start to concentrate on if we can get the biotics down and we can get the reliability up, then yeah, I think within 5 years, you'll be seeing a lot more people that have artificial limbs. I've seen, when I was in Tampa, I got to see the DECA arm, which is a 23 degree of motion, awesome robotic arm that's worth about $500,000. Yeah, we'd have to make it a little cheaper than that, but to just move those 23 degrees of motion and all of this stuff requires a lot of input and a lot of output. You can get that off the peripheral nerves, kind of, but if you had it coming straight from the brain, that would be you'd have even more ability to detect and also input. If I touch my finger, I feel it. It says, oh, I'm touching my finger. If I put a pin on it, I know I have pain. I don't think the DECA arm does that. So those are things that we're going to need these electrodes in with that interface into the brain to be at higher levels. So in 10 years, I think, yeah, we'll have 5 to 10 years, we'll start to have these levels that need to be able to reach multi-level parts of the brain. And that goes toward the mapping. We'll have to map the brain. For everybody has a little bit of a different brain. So each one of these devices will have to be inserted. They'd have to be able to map the brain. Then they'd have to be able to interact with it dynamically. And I think that's possible.
So with that, where do you see, I know it's hard to predict 50 years, right? But that's where everybody's, wanting to know, like, what's the age of the internet coming to fruition? What's the cybernetics piece? What's the brain actually capable of once you start putting science into it? The human mind is just something that's incredibly complex. Something that we've spent years trying to go through and understand and have years to go. So to have, cybernetics, to have movements, this all sounds, amazing. And it's things that we can see today. But, what's behind the green curtain? What do you see, the Wizard of Oz, what's he doing back there? What's 50 years look like for you?
Wow. Well, if we still have the neuroscientists working, by then I think we're going to have a better understanding of the brain than we do today. My old professor works on learning and memory. To me, the thing of the matrix would be, in 50 years, probably possible. If we have an understanding of how memories are made and how they're more or less formed, where they're formed, how they're formed, then you should be able to make them. Of course, that opens up a whole can of morality, but it also makes it so, in the movie The Matrix, of course, you had the woman, I can't remember her name right off the top of my head right now, but she was able to learn a helicopter, how to fly a helicopter in like 2 seconds. That kind of stuff I think would be possible if we have an understanding of the brain. And I think it is possible because we're going to have electrodes that enable us to map the brain and figure out all of those processes to be able to do that. So in 50 years, I think that will actually be a melding of man and machine. We'll be able to go much beyond what we are now. And at least that's my hope. But I also hope that we have the wisdom to be able to control our basal impulses and, not make it everybody, I'm going to program everybody. That's, arguments to be had during the whole process of this.
So the excitement that you have for human processes, what do you think, kind of just going into like the cuter aspect of it, right? So what about animals, different things like this, to go in and program, let's say maybe non-human primates to perform, certain tasks that we're doing for trainings. What about, different learnings, aspects of how we can expand or understand the animal world as opposed to what we have as an understanding today?
Well, I think your question would be happening before we get to that on humans. The neuroscientists, of course, will have to understand how these type of memory functions and how that type of thing works. The best thing to use would be something that would be able to partially communicate with us, the primates, higher level animals, that kind of thing. In that case, yeah, I think they will be able to more or less increase, as you say, the intelligence of those creatures as well, to the point where they may be at our level now. I mean, that's the way I see it.
So expanding on that just a little bit, are you saying that you would see primates talking to us with an understanding before we would have, like a matrix type level, world or simulation, I guess, if you will?
Well, I believe they actually talk to us now. I mean, we've had gorillas that learn sign language. So yeah, I think, if we have an understanding of how their brains work and they have a certain level of understanding of communication amongst themselves even, and they've shown that, then yeah, I think we can, have a way to where the machine helps them talk to us. So, yes.
So today we have a lot of marketing done by a well-known billionaire. Won't mention any names, but the most recent one that they've done really puts neuroscience into a field where I don't think people have been able to kind of think about it. It puts it at the kitchen table, if you will. What do you think as far as developments that would be existing today that can be something that like a kitchen table talk would make exciting? What do you find that we can use today to kind of have fun with neuroscience?
Well, I think, that he has put a lot of emphasis on where I think things can go, and created a lot of talk just about neuroscience that most people at the kitchen table would have never talked about. Neuroscience a couple of years ago wouldn't have been on anybody's tongue. But now people are like, well, that brain interface might be actually possible. And it might be possible I could actually answer my phone in my head. It may or may not be possible in 10 years, but that can be a probability that you wouldn't need a phone anymore. You can just, hey, dial up the phone and it's connected inside of you. That's the part of the brain-machine interface which is interesting. I think it's actually brought people out to understand that there are possibilities out there to where these type of interfaces and devices can take us. It's not just science fiction. It's not just, we're going to watch RoboCop and, that's that cyborg movie stuff. This actually might be possible. And so, yeah, I think individuals, and certain news has brought a certain light to what we're doing. And yeah, I appreciate it.
So that makes it seem very exciting for things that can be done, that are in the news that people haven't thought of. But as just like anything else, you have one project that gets told to the public, and then there's a lot of different things that are behind it that are even more advanced that we won't see for another 5 years. What do you feel comfortable saying that things can be done today that seem futuristic 5-10 years in advance that we have essentially the power to do today if it's not already being done?
Well, as neural interfaces are concerned, just a few years ago, we've been developing implants, so people that never could see before can actually see. They may not see as we do. They see shapes, and they can tell a doorway or something like that. But still, they can actually see. They were born blind, but now they can see. We have people today that can hear. More 10 years ago, 15 years ago, would have never been able to hear. People are walking with different types of robotic arms and legs, and learning how to use the peripheral nervous system to communicate with those types of devices. All of that stuff, I think, 10 years ago was thought of as science fiction. But yet, many years now at SFN and at the Neural Interface Conference, they brought people in that have these implants that actually show, hey, I've got this cool robotic arm. You would have never seen that 10 years ago. So yeah, I think there's a lot of things that we've done and that we've shown in neuroscience and in neurotechnology that have enabled people to live better lives.
So with that being said, it's amazing to have devices that go through and help people that need the help. But I'm a little selfish. I don't need the help. What can those devices do? You think, what could they do for me?
Well, I think they can do a lot for you, depending on where you want to go with it. Some people aren't going to want to have something put into their heads, but if you want to have something put into your head, I think a lot of things can be done. You could actually, like I said, you could control different types of computers just with your thoughts alone. This has already been shown to actually be with people that have locked-in syndromes. They can actually control the computer just with their thoughts. Even with a skull cap full of electrodes, you can do certain things that 10 years ago, 15 years ago, you wouldn't be able to do. That type of information is harder to get to because it's you're not hitting action potentials, you're hitting local field potentials. But you can turn all that information into somebody like you saying, I just want to sit here and relax and have, the movie shine in my head. Well, you're probably not going to do that with an electrode. But if you had an implant, we could put those visuals straight into your brain as long as we understood how they go in. That's where the neuroscience comes in. It figures out a way to interact and how all that works. And then the devices can be made that actually would put the images in your head so you can watch the movies or even have a virtual reality experience, let's say. So yeah, you could be selfish and we could still make things that are pretty cool, I think, that wouldn't be too terribly invasive.
Going a little bit deeper, if, let's say, humankind invented a time machine and gave you access to it, and you're yourself 50 or 100 years into the future, what would you come back and tell yourself today? What would you try and say that the future is doing for you?
Well, I would hope that a lot of the common things that people are suffering from, like Parkinson's, ALS, and that kind of stuff, would be of the past, or at least it would be under a controlled situation where we could have implants or a therapeutic type of implant that would be able to help people live longer and better lives. As for the selfish part, personally, I do like the idea of having, a faster way of learning. Learning is fun and great. I've done a lot of learning in my life, but being able to learn just a bit faster would be really nice. So yeah, I mean, I enjoyed my time in the learning memory lab that I was in with Dr. Weber and it was very, very interesting to me. I'm not very good at the neuroscience, but the technology level would be cool to be able to put that type of stuff into your head. Yeah, and I think in the future, I don't think people are going to really have to have amputations or anything else. They will have something that's robotic enough. Then it'll be like Luke Skywalker. You'll be able to have the cool arm that feels, put a pin and you'd be able to feel it. You wouldn't even know that, it's something that's not yours. So those kind of things I think will be part of the past, at least that's my hope, and that's why I'd like to try to develop this stuff and get it into humans so we can expand upon the promise of implants and the promise of neural implants.
So one of the things that I think about kind of when you're talking about all these different things, I think of what we're trying to do when we go to the moon or Mars, the different things that have been kind of in the news lately, right? And if you were to have some sort of like a bionic cyborg or robots, and then go through and have an implant that sees and feels everything that they're doing from that distance, the capabilities seem almost endless. So what would be something that, like, if you had like a magic lamp and a genie, what would you want to see, as far as those moonshot things with neuroscience?
Well, the moonshots. I think we're doing a lot of moonshots as we are now. One of the moonshots would be to try to figure out, at least in neuroscience, the brain mapping and how the brain works. To me, that was a big moonshot for the brain. Obama did a really good thing on putting that forth as one of the big moonshots, because until we understand the brain, a lot of the things that we're hoping for, we want, are never going to come to fruition. So developing the methods to figure out how to do all of that, I think, is paramount as part of the moonshot. Being able to communicate with different parts of the brain seamlessly, I think, is probably going to be something that needs to be part of that moonshot as well. Because a lot of things just aren't in one part of the brain, they're going on different parts of the brain. So we're going to have multiple implants, let's say, to be able to control one or two different types of things. That would be the moonshot for me. Because once we've got the brain more or less modeled, then we can start going into the smaller exploratory, hey, let's look at how memory works. Let's look at how this type of thing works. Sight. Can we visualize something that way we can make a movie in your head, or make an experience. You can go to like Total Recall You know, whatever you want to see, have a vacation from the vacation. So, anyway.
So what would you today tell your past self about all the different things that you've learned and all the different ways that you got to where you are today? Would there be anything that you would do different or change?
Oh, that's a good one. For the most part, you know, I got into this, and it wasn't my initial, it wasn't my initial choice to go into biology. I was starting out in power electronics and wanted to do electronics. But everything always happens, and you learn and you grow and you figure out new things, and you go, hey, that might be pretty cool. So at the time, I really don't think I would go back and tell myself anything differently other than, hey, just keep trying to learn everything you can about, different aspects of this, because it's not just this type of technology just isn't one thing. You have to start looking at biology. You have to learn how to interact with different types of people. It's multidisciplinary. And so it's been an interesting adventure all the way to me. So no, I wouldn't really tell myself anything different. Otherwise, I probably wouldn't be here telling you this today. So.
So what would be the one thing that you love most about the field? What kind of keeps you, getting up out of bed, excited for your day to day? What is it that you're waiting for to happen?
Well, apart from the jobs that I've had in the past of being a technician, this job always changes, and that's what makes it interesting. You'll have different things that you're looking at. You'll go, oh, maybe I need to go down this way. You'll find out that that way may not be the way. But during that investigation, you'll find different ways to branch out and solve the problem. There are times that's frustrating. Yeah, everybody has a frustrating part in their jobs. But to me, this type of job is always great because it's always new and fresh every day. And what I change, or I'm always just trying to say, I want to actually move this technology, not just for neuroscience, but I want to actually get us going into clinical and helping people with different aspects. So that's really what gets me out of the bed every day is I want to keep moving forward so I can say these devices are reliable enough. Now we can start looking at this human application.
Well, Chris, thank you for doing an interview with me. If we weren't during the COVID times, I would shake your hand. But unfortunately, I got to stay 6 feet apart from you. But thank you so much for doing this today. I learned a lot from you. It's been amazing. If there's, anything that I see happening in the future that I want implanted, you're my guy. So, but again, I'll toss it back over to Matt, and then thank you guys so much for having this webinar with us today.
All right, that was very interesting webinar here. We do have Chris and Lawrence here. If you have any questions, and another reminder that August 20th is going to be our next webinar. We are tentatively planning on having Andreas Talias here with us from Baylor College of Medicine. So pretty excited about that one too. Thanks everybody for joining us. Thanks Chris and Lawrence for that great interview.
Thank you.